Hello everyone, welcome back to our NDT training session. I am Muthulakshmi, quality expert, ASNT level 3 in 10 methods, APA, PMP and Frozio level 3 certification holder. Today we are going to deliver a critical aspect of magnetic particle testing, that are the types of magnetizing current and demagnetization techniques. Let's break down the different current types and their implications for NDT. Let's start the session. Understanding the different current types is essential for selecting the right magnetization technique for surface and subsurface defect detection. In magnetic particle testing, we use different types of electrical currents to create magnetic fields in our test object. The main types of alternating current, half wave direct current and full wave direct current and three-phase full wave direct current. Each type has unique characteristics, advantages and limitations, which we will explore slide by slide. Let's move on the next slide. First, we will discuss about the alternating current in magnetic particle testing. AC is a very common choice in MPT because it's readily available. Its availability is easily obtained or accessed, and it creates a effective surface magnetization due to something called the skin effect. This is called the skin effect. It typically operates at voltages from 120 volt to 440 volt and frequencies of 50 to 60 Hz depending on location. Then what are the key characteristics used in the alternating current? First one is waveform. It's a sine wave. Sine wave means this is a sine wave, meaning it has equal positive and negative halves within one complete cycle. So this is positive, this is negative, this is one, this is one. So equal positive and negative halves within one complete cycle. Then frequency, commonly 50 Hz in Europe or Asian countries or 60 Hz in USA. Magnetization, it produces a rapidly reversing magnetic field. It creates rapidly reversing the magnetic field, concentrating mostly on the surface. For surface breaking flaws but limited for subsurface cracks. Next, advantages. First one is skin effect. This is a major benefit. The magnetic flux concentrates at the surface of the part. This makes AC ideal for detecting surface crack. Mostly flux concentrate on the upper part of the material. This is called the surface. Think of it like a very shallow magnetic field that perfect for finding flaws right on the exterior. Second one is easy demagnetization. The reversible and alternating nature of AC makes demagnetization straightforward. We will discuss demagnetization in more detail shortly. But for now, know that AC helps in removing residual magnetism easily. Already we discussed about the residual magnetism. So AC helps to removing residual magnetism easily. So next one is particle agitation. The content of the particle agitation is the constant current reversals helps to shake the magnetic particles, which can improve the visibility of indications by allowing them to settle properly at defect sites. The next one is disadvantages. Limited penetration. Because of the skin effect, AC is not effective for subsurface discontinuities. For skin effect, if your defect is even slightly below the surface, AC won't reliably detect it because the poor subsurface detection, weak penetration due to surface concentration. Next one is not suitable for thick coatings. It cannot effectively penetrate coatings thicker than 0.08 mm to or 0.003 inches. This is crucial to remember for coated parts. Next one is timing sensitivity. It can be hard to control the exact moment of peak magnetization. This might be important for certain automated processes or specific procedures. Next one is restricted use. Some specifications may prohibit the use of AC on plated components. Always check your applicable standards. So next we move to the half wave direct current. Half wave DC is created by rectifying single phase AC, allowing the current to flow only in one direction due to positive half of each cycle. So here this is the half wave DC. So only positive side. This results in a pulsating unidirectional current which has unique advantages. Then key characteristics are, first one is waveform. It's a pulsating DC with current flowing only during the positive half. This is the positive half of each AC cycle. Imagine cutting off the bottom half of an AC sine wave. This is sine wave. So we cutting only the positive side. This is a half wave DC. Next one is flux distribution. The magnetic flux is 0 at the center of the object. If this is object, the center is always 0. The maximum is at surface. Maximum peak is surface, center is always 0. While it's DC, the pulsating nature affects its distribution. Next one is mobility. The pulsating current leads to high particle mobility, meaning the magnetic particles can move more freely and align effectively. The next is advantages. Main advantage is deep penetration. Half wave DC offers a deep penetration comparable to full wave DC, making it effective for detecting subsurface discontinuities. This is a significant improvement over AC. Next one is particle agitation. The pulsing effect enhances dry powder sensitivity. This is particularly useful when using dry magnetic particles, helping them gather at defect location. Next one is simple circuitry. It's relatively easy to integrate into portable or mobile AC equipments, making it convenient for field applications, especially for inspecting welds and castings. Next is disadvantages. Poor demagnetization. Half wave DC cannot reverse the current, which limits its use for demagnetizing the part after inspection. You would typically need another method. Next one is incomplete demagnetization with AC. If you try to demagnetize a part inspected with half wave DC using AC, it may not fully demagnetize. It may not be fully effective because AC's field is surface concentrated. while half wave DC is deeper penetration. This is, you see, half wave DC is deeper penetration. So we move the next slide. Next, full wave direct current. Full wave direct current is generated by rectifying both halves of an AC waveform. It producing a continuous pulsating DC current. It's available in both single phase and three phase configurations. Next we discuss about the key characteristics. First one is waveform. It pulses during both halves of AC cycle, effectively doubling the frequency compared to half wave DC. The next one is penetration. Offers deep flux penetration, making it suitable for detecting subsurface discontinuities. Next one is skin effect. It exhibits minimal skin effect compared to AC. This is a full wave direct current. Next we move the next slide. Advantages. Effective penetration. It provides the same depth effectiveness as three phase full wave direct current for single phase system. Next one is reversing demagnetization. Unlike half wave DC, full wave DC equipment can include switching circuits to reverse the current, allowing for efficient demagnetization. This is a major operational advantage. Next one is cost effective. Single phase full wave direct current equipment is generally more affordable than three phase system, which can be a deciding factor for some applications. Next is disadvantages. High power demand. The single phase units require 1.73 times more input current than three phase systems. This can be a limitation, especially at high amperages above 600 amperes. Next we discuss about three phase full wave direct current. This is a smoothest form of DC for magnetic particle testing. It's produced by rectifying all three phases of commercial AC power. It converts the negative cycle to positive, resulting in a nearly constant direct current output. So it's convert negative into positive. So here no negative current cycles. Next, key characteristics. Waveform. It's a smooth, nearly flat direct current with very minimal fluctuations. What is the source? It's derived from a three phase AC input. And the advantages. Balanced power load. It draws current evenly from all three phases, which minimizes imbalance on the power line. Next is lower line demand. Requires less input current per phase compared to single phase systems. This is important for industrial settings to avoid overload circuits. Next one is improved indication quality. It supports quick break circuits that can enhance detection at the ends of longitudinally magnetized parts. This means better, sharper indications. Better and sharper indications. Next is cost efficiency. By balancing the load, it helps to avoid utility penalties that can arise from unbalanced loads often seen with single phase equipment. Next, we will discuss about demagnetization in magnetic particle testing. After conducting an MPT inspection, removing any residual magnetism is often crucial. Demagnetization is essential to remove residual magnetism left in the test object. After magnetic particle inspection, why is this important? Residual magnetism can interfere with subsequent operations like machining, welding, or even accurate instrument readings. So it causes false indication in later inspection. Next, the factors influencing residual magnetism. Not all materials retain magnetism equally. What are the material types? Low carbon steel and hardened alloy steels. In low carbon steel, this material retains minimal magnetism. It's relatively easy to demagnetize. In hardened alloy steels, these materials retain strong magnetic fields for extended period. They are much harder to demagnetize due to their higher retentivity and cohesive force. This hardened alloy steel has higher retentivity. Already we discussed what is the retentivity and what is the cohesive force, that all details. And then material condition, the condition of the material affects how easily magnetism can be removed. For instance, materials that have been cold worked or hardened will retain more magnetism. This is the material condition. Next, what are the demagnetization methods? First one is heating to Curie temperature. This method involves heating the material above its Curie temperature. First, we all know what is Curie temperature. Curie temperature is nothing but at which a ferromagnetic material loses its magnetic properties and becomes paramagnetic. This is a Curie temperature. So, heating to Curie temperature means heating the material above its Curie temperature. At this specific temperature, the material loses its ferromagnetic properties entirely, effectively destroying all residual magnetism. This method is generally used when heat treatment is already part of manufacturing process, as it involves significant heating. So this is the first method for demagnetization. Next one is reverse electromagnetization. This is most common method. This is the most prevalent method in NDT. It involves applying on alternating magnetic field that gradually reduces in intensity and reverses direction. It involves applying a magnetic field that alternates in direction and gradually decrease in strength, which randomizes the magnetic domains and it removes residual magnetism from the part. This is the reverse electromagnetization. Next one is typical process. You would typically pass the object through a coil carrying AC. As the object moves away from the coil or as the current is slowly reduced, the alternating field repeatedly magnetizes and demagnetizes the path with decreasing strength, eventually leaving it demagnetized. The same principle can also be achieved using DC with a similar gradual reduction and reversal of field. Understanding these different current types and demagnetization techniques is fundamental for any NDT professional. It allows you to select the correct method for the material and the type of discontinuity you are looking for, and to properly prepare the part for subsequent processes. And I will prepare some questions for this session. Comment your answers in the comment box. I hope this concept is now clear to everyone. If you have any further clarification, comment on comment box. Thank you.